In this part of chapter 17, we're going to begin talking about titrations. So to begin with, we're going to start with a review of neutralization reactions, and then we will follow with the description of the treatment of strong acid, strong base titration. In later videos, we will have the description of the titration process for a weak acid or weak base with a strong acid or strong base. So let's get started. All right, so you guys might remember that in General Chemistry 1, you talked about neutralization titrations, where basically you would have an analyte that had an unknown concentration. And what you wanted to do through that titration was to figure out its concentration. To do that, you added a pH indicator, a few drops of it, and then you started titrating by adding what is known as a titrant. That titrant is a standard solution of which you know the identity and you know the concentration of it. And you would add that titrant until the point where the pH indicator would change color, which would indicate that you had reached the end point of the titration. The endpoint of the titration would basically give you the number of moles of the titrant that you had added, and from those moles of the titrant, you then could calculate the number of moles of the analyte that you began with. And since you knew the volume of it, you could now calculate the molarity of it by taking the moles divided by the liters. That endpoint of the titration, which is the point where the color changes, is related to the equivalence point, meaning the point at which we have an equivalence in the number of moles of the analyte versus those of the titrant. But they're not exactly the same, and we'll get into more details about this in later slides. Now, in this particular chapter, we're going to be looking at titrations from a different angle. We're no longer interested only on figuring out the concentration of the analyte. In fact, what we're going to be doing actually is looking at the changes in the pH during the titration process. So we want to be able to follow what's happening at every step in the titration. For example, here we are beginning with an analyte. Let's say that it is HCl, hydrochloric acid, and that analyte is going to be titrated with our titrant, which in this particular case is going to be sodium hydroxide. As we know, the reaction of hydrochloric acid with sodium hydroxide would lead to the formation of a salt, sodium chloride, and water. And what we're going to be doing is that we're going to be measuring the pH throughout the titration process. So at the beginning, before we add any titrant, all that we have is hydrochloric acid, and because of that, the pH is low. As we start adding titrant, the pH is going to increase as shown on the right hand side in what's known as a titration curve. And so we're going to be following the pH as a function of the volume of the titrant that is added. And what we're going to be doing in this video for the most part is learning how to calculate the pH at the various stages within this titration curve. At the beginning, before titrant is added, then in this region between the beginning and the equivalence point, at the equivalence point, and then after the equivalence point. Another thing that I need you guys to remember is that whenever you are doing a titration or a neutralization reaction, the equivalence point is the point at which you have added just enough moles of the titrant to completely react with all of the analyte that was in that solution. So basically what we're saying is that we have added enough titrant to react exactly with the substance that is being titrated. For example, if we had 1 mole of hydrochloric acid, since the balanced equation tells me that the ratio is a 1:1 because of the coefficients, then the equivalence point would be reached whenever we have a 1:1 molar ratio of the hydrochloric acid to the sodium hydroxide. On the other hand, let's say that for some reason I'm titrating hydrochloric acid with calcium hydroxide. You can see that the balanced equation tells us that for every 2 moles of hydrochloric acid, we have to add 1 mole of calcium hydroxide. And so in that particular case, the molar ratio at the equivalence point would not be a 1-to-1, but instead it would be a 2-to-1 molar ratio, right? So again, the equivalence point is basically at which point you have stoichiometric equivalence between that acid and base that are being neutralized. All right, so having said that, let's go ahead and begin by looking at the titration of a strong acid with a strong base or a strong base with a strong acid. This is section 17.3 of your book. Okay, the first thing that we need to know in the titration of a strong acid with a strong base or strong base with strong acid is the fact that there is no equilibrium. Basically, the reactants are going to completely be consumed as much as they can, and we're going to have a one-sided arrow. Basically, the reaction proceeds to completion, no equilibrium. As we know already, whenever you react an acid and a base, in a neutralization, you're going to end up forming a salt and water, and 2 examples of that are shown here at the bottom. So hydrochloric acid with sodium hydroxide leads to the formation of sodium chloride and water, and I just want to remind you again that the product is formed by taking the cation from the base and putting it together with the anion of the acid to form the salt, and then what you're left with is the cation from the acid and the anion from the base to form the water. We can see that again here with sulfuric acid reacting with calcium hydroxide. They react to form calcium sulfate, which again is utilizing the cation from the base and the anion from the acid, which come together to form the salt. And then what we're left with is water. And again, notice the single-sided arrow indicating that the reaction goes to completion, and we do not have to we don't have to do equilibrium calculations because there is no equilibrium. All right, so this is what a titration curve would look like for a strong acid and strong base. And for the purpose of this demonstration, we're going to be talking about hydrochloric acid reacting with sodium hydroxide to form sodium chloride and water. As a side note, I want to say right now, you need to make sure that you know your strong acids and strong bases, because the problem is not going to tell you that you are titrating a strong acid with a strong base. It is just going to tell you that you are titrating or reacting something like hydrochloric acid and sodium hydroxide, or something like nitric acid and potassium hydroxide. And you need to be able to identify that that is a strong acid, strong base titration. All right, the next thing that I want us to see is the titration curve. In the titration curve, you're going to have pH on the y-axis, and on the x-axis, you have the milliliters of the titrant. Basically, how much of the titrant you have added into the analyte solution. Notice that we're starting at a low pH because we're starting with just the acid in the beaker. Let's say I'm going to draw my beaker here. That beaker has HCl. And we are adding the titrant through a burette. In this case, that's going to be our sodium hydroxide, and we added drop-wise, specific volumes that get added. All right, so at point A, all that I have is just the acid. I have added 0 of my sodium hydroxide, so all that I have is the acid. And that point A is what's known as the initial point, where you only have acid in this particular case, or base only if you were titrating a strong base with a strong acid, which is not the case in this particular example. So here we just have acid, and we already know that to calculate the pH of a strong acid, we just take the negative log of the hydrogen ion concentration. After that, we begin adding titrant, and this region B is known as the region of partial neutralization, where basically you have not completely finished or used up all of the HCl, because I have a lot of HCl and I've only added a little bit of the sodium hydroxide. All of the sodium hydroxide that I add in that range is going to be consumed, and in doing so, it will be consuming some of the HCl, but you would still have HCl in excess. So I'm going to go and write that here just for you to have it. HCl in excess I mean excess as in that there's leftover, but I will be writing it as XS just to make it simple for me to write. And so yes, so in this range, basically you still have leftover hydrochloric acid. All of the sodium hydroxide that has been added has completely reacted, and in doing so, it has formed some salt and some water. After that, we get to what's known as the equivalence point, which we said is the point where we have an equivalent number of moles of the acid to the base. And in this particular reaction, that is a 1-to-1 molar ratio. So we have just as many moles of hydrochloric acid as we have added moles of sodium hydroxide. And because of that, they completely consume one another. So in reality, we have 0 HCl and 0 sodium hydroxide left, and all that is left is sodium chloride and water. Water is neutral, sodium chloride is a neutral salt, and because of that, the equivalence point of a strong acid, strong base titration will always be 7. It will be neutral. So that's something for you to write down or to notice that the pH at the equivalence point for a strong acid, strong base titration will always be equal to 7. Again, because the acid and the base have completely consumed one another, and all that you have left is the neutral salt and water, which generate a neutral solution. After the equivalence point, if we keep adding titrant, what's going to happen is that there's no more HCl, right? Because by the time we got to C, all of the HCl had been reacted, but we kept adding sodium hydroxide. So what we end up having is an excess of sodium hydroxide, and I'm going to write that here. The NaOH is going to be in excess, and because of that, the pH is going to be greater than 7. And the way to calculate the pH in this range is to find how many moles of sodium hydroxide excess we have, convert that into a molarity, and from there be able to calculate the pOH and later the pH. Another thing that I want to point out before we move on from this slide is that I want you to become very familiar with the shape of this titration curve. I want you to notice that when you're titrating a strong acid with a strong base, you're typically going to have a slow rise here at the beginning. Then you're going to have a very sharp increase in the pH as you are approaching the equivalence point and immediately after that equivalence point. And then again, the pH will kind of level off after the equivalence point. So do become familiar with the shape of that curve. In the next video, we're going to be talking about the weak acid, strong base, or weak base, strong acid titration. And those are going to have a little bit of a different look to them because of the behavior of the weak acid or weak base titration. So I do want you to be able to differentiate the behavior of the two different types of titrations. Also, I want to point out that your online book has a video which is embedded into figure 17.6 that shows you what's happening at the molecular level throughout the titration. And I encourage you to watch it because it's a little bit easier than just looking at these figures right now. All right, so we're going to start going through each of those stages. A, B, C, and D, and we're going to be talking about how to calculate the pH at each of those stages. So to begin with, stage A, which is at the very beginning of the titration. This is before you have added any titrant, before any base is added. So as we said, at that point, the only thing that we have is the acid that you're starting with in this particular case. Or if you were titrating a base with a strong acid, then all that you would have would be the base. So if all that you have is acid, then you can directly calculate the pH by taking the negative log of the hydrogen ion concentration. And the hydrogen ion concentration is derived directly from the concentration of the acid. Because if it is a strong acid, all of the hydrogen is donated. All of the hydrogen ions are donated. All of the acidic hydrogens are donated, I should say. All right, now if we have just base, then you can directly calculate the pOH by taking the negative log of the hydroxide ion concentration and then utilizing the equation that says that the pH is going to be equal to 14 minus the pOH. This right here is nothing different than what we talked about in the previous chapter about calculating the pH of a strong acid or the pH of a strong base. It's exactly these two things. All right, now we go to point B, which is in between the initial point and the equivalence point. We mentioned that that region is known as the region of partial neutralization because basically you have added some titrant and you have neutralized some of the acid or some of the starting analyte, but not all of it. And so what you're going to have is you're going to have an excess of your analyte, whichever one it is. In this particular case, we're showing the titration of an acid with a base, so you would have an excess of the acid that is in your beaker, right? You have not added enough of the base to completely consume it. So what you're going to do is that you're going to use what is known as an ICR chart, which is done in moles, in order to find the number of moles that are in excess for that acid. And then once you have that, you're going to be dividing it by the total volume of the mixture. And when I talk about the volume of the mixture, I mean the volume of the acid that you initially had in the beaker, plus the volume of the base that you have added through the burette. So it's the combination of both volumes of the acid or base. That's the new volume that you have in the beaker, basically, right? And so that's the reason why we use it in order to calculate the new molarity of the excess substance, which in this particular case is the acid. So we take the moles of the excess and we divide it by the volume of the mixture. If the excess was acid, as in this particular example, then you would find the pH of the solution by taking the negative log of the hydrogen ion concentration in excess. And if the excess was a base, if we had a different problem, then you would find the pOH by taking the negative log of the hydroxide ion concentration that is in excess, and then subtracting that pOH from 14 in order to find the pH. Now, the next point is the equivalence point. Remember that the equivalence point is the point where we have equivalent number of moles of the acid to the base. In this particular case, this is a 1-to-1 molar ratio, which means that we have an equal number of moles of hydrochloric acid to the moles of sodium hydroxide. And as we said already, at the equivalence point, these two completely neutralize one another. So they completely react, they are gone, and all that we have in the solution is the salt and the water, which are the products of that neutralization. Now, water is neutral, sodium chloride or any salt that is formed from a strong acid and a strong base is going to be a neutral salt, and because of that, the solution is going to be neutral, meaning that the pH is going to be equal to 7, and we actually don't have to do any calculations. So this is only for the equivalence point of a strong acid, strong base titration. So make sure that you don't confuse it, because for a weak acid or weak base titration, the pH will not be 7. And I'm going to go ahead and write this down. Only for strong acid, strong base, or a strong base, strong acid titration. Not for a weak acid or a weak base titration. All right, after that we have the last stage, which is D, which is what happens after the equivalence point. Remember that once you got to the equivalence point, you completely consumed the hydrochloric acid, but you kept adding more base. So now you're going to have an excess of the sodium hydroxide. Because of that, we need to find out what is the number of moles of that excess substance that we have. And to do that, the easiest way is to set up an ICR chart, which is basically a table to do a counting of the moles of the substances that we're starting with, how much we're adding, how much gets consumed, and how much is left as a result. And then once we know the number of moles, we're going to use the volume of the mixture to find the excess concentration. Again, the volume of the mixture is the sum of the volume of the acid plus the volume of the base, because those two together are now in the same beaker. And we use that new volume in order to calculate the molarity of the substance that is in excess by taking the moles in excess divided by the volume of the mixture. And now, if the excess was the acid, then you can directly calculate the pH by taking the negative log of that hydrogen ion excess and molarity, I should say. And if the excess is base, you would calculate first the pOH by taking the negative log of the hydroxide ion concentration in excess and then subtracting it from 14 in order to find the pH. All right, so we're going to look at the titration of a strong base with a strong acid. So this is basically the opposite. In this particular case, what we're starting with is, let's say, sodium hydroxide. And what we're doing is that we're adding acid as a titrant to it. So of course, in the beaker, initially my pH is high because I'm starting with a base. That pH is going to begin to be lowered as I add some of the titrant. Then there's going to be a sharp decrease in the pH as I approach the equivalence point and as I go past the equivalence point. And then the pH will continue to level off just like with the other titration, except that now at the end I'm going to have a low pH because I have now HCl in excess. Notice again that at the equivalence point, the pH is also equal to 7 because, again, I'm reacting a strong base with a strong acid. The products of that are salt and water, and specifically we're forming a neutral salt, which means that there's nothing acidic and nothing basic at that equivalence point. So again, remember, for a strong acid, strong base, or a strong base, strong acid titration, at the equivalence point, the pH is equal to 7. Notice the shape, compare it to the previous figure that we have for the titration of a strong acid and strong base, and notice that there's a lot of similarities except that the pH is going to start high and is going to go lower. Now, in terms of calculations, it is the same exact process that we had on the previous 4 slides. You saw in the previous 4 slides, I had the content for whether you have excess acid or excess base. So you're just going to be using the other equation that we didn't use. All right, so now we're going to start doing problems. And so in this particular slide, I have basically written down the process that we're going to follow to solve the pH for every stage in the titration. To do that, what we're going to do is to calculate the number of moles of acid and base. And I'm going to go ahead and say something right here in regard to this. In a lot of the problems, we're going to be dealing with molarities for the concentration and milliliters instead of liters for the volume, because we typically add small volumes, so milliliter is the unit of choice. And I'm going to put here on the left-hand side, you guys remember that molarity is the moles divided by the liter. Well, I don't really want to work with liters because I would have to do conversions several times in these kind of problems. And so I'm going to be working with milliliters instead. And so in order to be able to work with milliliters, what we're going to do is that we're going to say that now molarity is going to be equal to the millimoles divided by the milliliters. And I can do that because to convert between moles and millimoles, I would have to multiply by 1,000. And in order to convert from liters to milliliters, I would have to multiply by 1,000. And so the 1,000 that I use in both cases is going to cancel each other, and that ratio will still equal to the molarity. So whenever you're trying to work with molarity and milliliters, we can actually multiply these two in order to find the millimoles. And I will be solving the problems myself by utilizing millimoles instead of converting everything to liters and then to moles and work with like 0.000 moles of something. So it just makes the math a little bit easier. I encourage you to become familiar with this. Okay, so we will be calculating the number of moles of acid and base by taking the molarity, multiplying it by the milliliters in order to find the number of millimoles. Oops. All right, of the acid or the base. Step number 2 is that we're going to determine which component is in excess, whether the acid or the base. And based on that, we're going to determine whether we are in stage A, B, C, or D. A is at the beginning where all that you have is either an acid or a base. B is in the partial neutralization region. C is going to be your equivalence point at which we know the pH is equal to 7, and then D is after the equivalence point. If needed for stages B or D, you will use then an ICR chart in order to calculate the number of moles that are in excess. There's other ways other than the ICR chart. As long as you do the accounting on the moles, you don't actually have to have an ICR chart. So just to let you know, we're just going to do it to have an organized way to look at the number of moles that are left over. Once we know the number of those moles in excess, we're going to determine the volume of the mixture by adding the volume of the acid plus the volume of the base. We're then going to calculate the concentration of the excess component by taking, in our case, we're going to be taking the millimoles divided by the milliliters. And then finally, we're going to calculate the pH by taking the negative log of the hydrogen ion concentration, or finding the pOH first and then converting it to a pH if what we had left was the base. As a reminder again, if the number of moles of acid or base are equal, meaning that if you're at the equivalence point, then the solution pH is equal to 7. All right, let's get started with the first problem. So what we have is a 20 milliliter sample of 0.2 molar HBr, and in this particular problem, we are titrating that hydrobromic acid with sodium hydroxide, specifically 0.2 molar sodium hydroxide. And the question is to calculate the pH of the solution after the following volumes of base have been added. All right, so we know the volume and we know the molarity of the hydrobromic acid. We know the molarity of the titrant, which is the NaOH, and we know the volume of that titrant, which is going to be changing for every single part of the problem. All right, so to begin with, as we said, we're going to be calculating the number of moles. And if you don't mind, I'm going to do the first calculation for HBr. So the moles of HBr that we are beginning with is going to be equals to, and as I mentioned, I'm going to be working with millimoles, so sorry about that, millimoles of HBr are going to be equal to my molarity times the milliliters. So that's going to be equal to the 0.200 molar times the volume, which is 20.0 milliliters. And that is equal to, let's see, where are you? 4.00 millimole. Awesome. We're going to be using this number in most of the problems, so I just wanted to go ahead and calculate that and have that kind of ready for us for when we need it. So remember, the number of moles of the hydrobromic acid or the analyte that we are beginning is 4 moles, millimoles. All right, so let's talk about point number 1. So at point number 1, I obviously have HBr. I have 4.00 millimoles of HBr, but I have added 0 milliliters of my base. So all that I have is that hydrobromic acid. There is no base, and if you look at your notes, what it said is that for that stage A, so I'm going to go ahead and label it, this is stage A. For that stage A, you could directly go and calculate the pH by taking the negative log of the hydrogen ion concentration. And so for this particular case, I actually don't need the millimoles. What I need is the molarity. And I can just go back and use the molarity of that hydrobromic acid, because you know that the hydrobromic acid will completely dissociate, giving us 0.2 molars of hydrogen ion and 0.2 molar of bromide ion. So I can just come and plug in that 0.2. So the pH is equal to the negative log of 0.200, and that gives us a pH of 0.699. And we are done with this particular problem. Significant figures, remember that if you're starting with 3 significant figures on your concentration, then your pH needs to have 3 digits after the decimal point, and that's what we have. As a check, notice that we have a very low pH, which would make sense for a fairly concentrated, strong acid solution. Now, as we should expect, as we add base to that solution, we should see the pH rise. So we go now to point number 2. And at point number 2, we have added 15 milliliters of the base. So what I'm going to do now is that I'm going to rewrite the number of moles of HBr that I have. My HBr, it's still 4.00 millimoles. That is in the beaker. That is not going to change in between the problems. But now I have added 15 milliliters of, let me see, significant figure, sorry, 15.0 milliliters of NaOH. And so my job now is going to be to find the number of millimoles of NaOH that are added. So for that NaOH, I'm going to be taking, oh, just as a side note, I'm in front of a window and a hawk just stopped on the tree in front of my window. Sorry for the distraction, but that is amazing. Woohoo. All right, let's try to continue. So sodium hydroxide, I'm going to calculate the number of millimoles of it by taking the molarity and multiplying it by the volume in milliliters. So I'm going to take my 15 milliliters and I'm going to multiply it by the molarity of that sodium hydroxide, which was also 0.200 molar. And because of that, we have a total of 3.00 millimole of sodium hydroxide that have been added. So then we compare the moles of the acid to the moles of the base, and we see that the moles of the base is smaller. So on my titration curve, if this was my titration curve, and this is the shape of a normal titration for a strong acid with strong base titration, I'm no longer at point A because point A is where I have added 0 milliliters of that sodium hydroxide. But I am not quite at the equivalence point because at the equivalence point, I would have the same number of moles of the two. So what that means is that I am in the region here in between the star and the equivalence point, which we said was region B. For region B, what we said that we would do is that we were going to use an ICR chart in order to figure out the moles that are in excess. And again, that's not the only way to do it. In fact, I'll tell you a faster way to do it in a second, but I just want you to see where these numbers are coming from. So what we're going to do is that we're going to write an equation for the neutralization. So we're going to take HBr plus NaOH, and we're going to say that the product of that is going to be the salt, which is going to be the sodium bromide. Remember that I take the cation from the base and the anion from the acid and put them together. And then the other product is going to be water. And the ICR chart is basically the number of moles that I am beginning with, which for HBr is 4.00. For the sodium hydroxide, it is 3.00. And for my products, it is 0 and 0. We then are going to say that the change is that all of the limiting reactant will be reacted, meaning out of these two things, whichever one is the smaller, it will be completely reacted. So 3 is smaller, so I'm going to therefore say that my change is going to be negative 3.00 so that it all gets used up. And that change carries to the HBr. So the same amount would be subtracted here, leaving us with now a total of 1.00 millimoles of the hydrobromic acid. And the change also happens for the products, although we don't really care because the products do not affect the pH. We have a neutral salt and we have water, which, as we know, we don't include in any kind of calculation. So in the end, this is the number of moles that you have, but the sodium bromide does not have any effect. So what we cared about was the number of moles of HBr that remained. This is the millimoles of HBr in excess. And as I mentioned, there's an easier way to calculate that without doing an ICR chart, which is basically just to take the number of moles that you're starting with and subtract the number of moles that react without writing all of this down. But I just wanted you to see where those numbers come from. And Again, remember that when I put XS, that means that I'm talking about the excess. It's just my way of abbreviating that. And so we have a total of 1.00 millimoles. Now I'm trying to calculate pH, and as I know, the pH is the negative log of the hydrogen ion concentration. And so I need a concentration, not just moles. And to find the molarity, I need a volume. Specifically, I need the volume of the mixture, which is basically the sum of the volume of the hydrobromic acid that we began with, which if we go up here to the problem, we started with 20 milliliters of HBr. I'm going to write that here, 20.0 milliliters. And to that, we added base. Specifically, we added 15 milliliters of base, so 15.00 milliliters. And our total volume is then a total of 35.0 milliliters. I can now calculate the concentration, the molarity of that HBr in excess, which is going to be the number of the millimoles, 1.00 millimoles, and dividing it by the milliliters, 35.0 milliliters, and the answer to the molarity is therefore 0.0286, and that's molar. And since HBr is a strong acid, it will completely dissociate in solution, meaning that the concentration of the HBr is equal to the concentration of the hydrogen ion in the solution. And so therefore now I can find my pH by taking the negative log of that hydrogen ion concentration in the solution, which was 0.0286, and that gives me a number which is 1.544. 3 significant figures, 3 decimal places on our answer, and we are done with the second part. Again, a reality check. So in the previous problem, or in part number 1, I should say, the starting pH was a 0.699. As we expected, as we started adding some of the titrant, which is a base, the pH is expected to rise a little bit, and it has in fact. All right, number 3 is whenever we have added 19.9 milliliters. And for 19.9 milliliters, you will find that you are still in region B. So I'm not actually going to do the problem. I'm going to let you do the calculations, and I will tell you what the answer is for you to check yourself. So for number 3, you're still in stage B, and the answer, in stage B, you would follow the same process that we did here on the previous part, and the answer would be that the pH is equal to 3.30. So please give it a try. Make sure that you in fact get to this answer, and if you don't, please reach out and I'll be happy to work with you. All right, now we go to number 4, where we have now added a total volume for NaOH of 20.0 milliliters. Remember that for this particular problem, for HBr, we started with a total of 4.00 millimoles. And now for the NaOH, we have added a total of, let's say, 20.0 milliliters times the molarity of it, which was 0.200 molar. That gives me the number of millimoles, which happens to be 4.00 millimoles. Notice that we have the same number of moles of the hydrobromic acid, which is the analyte, and of the titrant, which is sodium hydroxide. Because of that, that means that we are at the equivalence point, since we have an equivalent, a stoichiometrically equivalent number of moles of the two, and therefore we know that for the case of a strong acid and strong base, the pH is going to be equal to 7. And so there's no need for us to do calculations. We are in fact done with that part of the problem. And now we go to part 5 of the problem, where we have added 20.1 milliliters of sodium hydroxide, which is our titrant. So again, remember that for HBr, we still began with 4.00 millimoles. That has not changed. Now for the sodium hydroxide, we have a new number of millimoles, which is calculated by taking the volume, 20.1 milliliters, multiplying it by the molarity, which was 0.200 molar, and that is equal to a total of 4.02 millimoles. All right. Next, what we need to figure out is which of the substances is in excess and by how much. And hopefully you can see already that just by looking at these two numbers, you're able to figure out that sodium hydroxide is in excess and that the excess would be 0.02. But if you cannot see that, I encourage you to do an ICR chart where again you take the HBr, you reacted it with sodium hydroxide, you form your products, which are going to be sodium bromide and water. And mainly we're interested in what happens to the reactants. So initially for the reactants, I have 4.00 millimoles. For sodium hydroxide, I have 4.02 millimoles and 0 for my products. I then have a change. The change is that whichever one is the smaller one is going to be completely consumed. And in this case, it is my analyte, the HBr, that is completely consumed. And it goes to 0 for the result. Oops, that was supposed to be an R. And now the change is going to be the same for all of the reactants, so negative 4.00, which tells us that the excess for sodium hydroxide is going to be 0.02 millimoles. And for the products, yes, we're going to be forming positive 4.00, which means that we are left now with 4.00 millimoles of sodium bromide, and for water, we don't really care. Now remember that the sodium bromide does not affect the pH because it is a neutral salt, and therefore we don't really care for it right now. What we did need was the number of millimoles in excess for either of the two reactants. In this particular case, we have an excess of the base, and so we need to deal with that. So I'm going to just rewrite it. The millimoles of NaOH that are in excess is equal to 0.02 millimoles. And from that information, I need to get to a pH. Since what I'm working with is sodium hydroxide, what I can do is that I can convert this into a molarity, and from that molarity of sodium hydroxide, I can find the concentration of hydroxide ions. Once I have the concentration of hydroxide ions, I can find the pOH, and then I can convert that into a pH. So to find the molarity of sodium hydroxide, I'm going to need a volume, and this is the volume of the mixture. The volume of the mixture, again, is the volume of the acid that we're starting with, which is at 20.0 milliliters. And to that, we added now 20.1 milliliters of the base, sodium hydroxide. And so our total volume is going to be 40.1 milliliters. And now we can utilize that information together with the millimoles to find the molarity of that sodium hydroxide in excess, which is basically the millimoles, 0.02 millimole, divided by the 40.1 milliliters. And that gives us a molarity that is 5 times 10 to the minus 4. Oops. And that is in molar units. Remember, millimoles divided by milliliters is equal to molarity. And that, since it's sodium hydroxide, which is a strong base, that means that this is equal to the hydroxide ion concentration. So now that I have that, I can find the pOH by taking the negative log of that hydroxide ion concentration, which is 5 times 10 to the minus 4, minus 4, not 14. And that gives me a value of 3.3. And finally, from that, I can now calculate the pH, which is going to be equal to 14 minus 3.3. And that is equal to 10.7. And as always, I encourage you to do a reality check. In this particular case, we are actually after the equivalence point. And if you remember, at the equivalence point, the pH was 7. So it does make sense that it has increased. And remember that in the strong acid, strong base titration, there's a sharp increase in the pH immediately after the equivalence point. So it does make sense that we went really fast from a 7 to a 10.7. So it looks good. Now, number 6 is actually going to be also after the equivalence point. And as I did previously, what I'm going to do is that I'm going to give you the answer and I'm going to have you work at it at home to make sure that you get the right value. The answer for part 6 is that the pH is going to be equal to 12.737. Again, I highly encourage you to do it to make sure that you understand the process. And if you have any problems, please let me know. I'll be happy to work with you. All right, so that is a full titration for a strong acid and strong base. The process would be almost identical for a strong base that is titrating with a strong acid, except that at the beginning, you would have excess of the base instead of the acid, and at the end, you would have excess of the acid instead of the base. But the process will be the same, and you can use the slides that were previous to this problem to guide you through each of the steps. All right, the next part is questions for you guys. So first question. A 50 milliliter sample of HCl is titrated with sodium hydroxide. And okay, let me highlight 50 milliliter, which is 0.5 molar HCl, is titrated with 0.5 molar sodium hydroxide. So notice the same concentration. After 28 milliliters of sodium hydroxide are added, which of the following statements is true? The pH of the solution is less than 7, or the pH of the solution is equal to 7 or greater than 7, or we need more information. Give it a try. Pause the video. Come on, do it. All right, so in this case, you actually didn't have to do any calculations, although you could. But in this particular case, since we have the same concentration of the acid or the base, we can just look at the volume of the two to know which one is in excess. In this particular case, we have a higher volume of the acid, which is the analyte. And so that means that even after I have added the 28 milliliters of NaOH, there's still going to be an excess of the HCl. And because the HCl is in excess, that also means that the solution is going to be acidic. And so the pH is going to be less than 7 at this particular point. You could have gone and actually done the calculation for determining the pH. And to do that, you would take the milliliters times the molarity in order to give you the millimoles. You would do the same thing for the sodium hydroxide. The molarity times the milliliters would give you the millimoles. You could then find the number of millimoles that were in excess for the HCl. Once you had the millimoles in excess for HCl, you could convert it into a molarity by dividing by the mixture volume, which is 50 plus 28, so 78 milliliters. You would then take the negative log of that concentration, because that concentration is effectively the hydrogen ion concentration, and that would give you the pH. So you could actually find what that value is, but you didn't need to do that because all that you needed to look at in this case was the milliliters of the solution and figure out which of the two is in excess. That is it. All right, next question for you guys. Which of the following will produce a titration mixture with a pH of 7 at the equivalence point? Go ahead and pause the video and give it a try. All right, so the answer for this particular case is the fact that if we have a pH of 7 at the equivalence point, what that means is that we are titrating a strong acid with a strong base, or a strong base with a strong acid. So our job was to look at the options here and see which of those was basically a mixture of a strong acid and a strong base. This right here is acetic acid, which is a weak acid, so that's a no. Out of these two, ammonia is a weak base, so that would not work. Out of this, actually both of those are weak. This is a hydrocyanic acid, which is a weak acid, and this is pyridine, which is a weak base. So the answer was D, which is where we have nitric acid, which is a strong acid, and lithium hydroxide, which is a strong base.